Thank you, Dalton, for the introduction, and also thank you the programming committee for the invitation. And I'm very honored here today to present some of the work that I've been doing the last couple of years. And you can access the slides by scanning the QR code or visiting the URL at the bottom there, bit.ly/GeoAI-talk. And here's the outline. First, I'm going to briefly introduce Open Geospatial Solutions, a GitHub organization that I created for hosting open source geospatial packages. And then I will introduce Google Sensing and GMap, and particularly some of the tools that are relevant to AI and also GeoAI. Then I will talk about segment geospatial, how you can use that to do image segmentation on remote sensing imagery. And lastly, I will show you some additional resources. And there are going to be a lot of links, a lot of demos, but you will not see any source code. So I'm trying to basically give you some impression what kind of things you can do, and then later you can always dive deep into some of the resources that I provided. If you have any questions during my talk, feel free to raise your hand. If you have quick questions, we can address earlier, but at the end, we certainly have questions, time for question and answers. And so for this talk, we highlight these two packages that I created. One is called GMap, the other one is called SamGeo. And so this is a GitHub organization that I created about a year ago. So some of the most popular ones, including GMap, LeafMap, and also Segment Geospatial. You can scan the QR code to go to the GitHub organization. And these are some of the packages, data catalog, and also interactive web app, and some of the resources. So my mission is to make geospatial data, especially big data, more accessible. Kind of like my goal is to teach people how to watch movies for free, but in the geospatial domain, how to stream geospatial data, how to do computation for free without paying anything. So utilize those free cloud computing resources. So if there's a take-home message from my talk, that's it. So show people how to watch movies, show people how to stream geospatial data and running computation. So most of my packages utilizing the Python programming languages, but there's also R and also some ArcGIS toolbox and also data catalog. So nowadays there's a lot of data, geospatial data in the cloud, but not many people have the skills how to actually to stream the data, how to do computation. And many of the people in the geospatial community are still trying to downloading data to their desktop computer, trying to do data processing. It's probably still works fine right now, but in a couple of years, you probably not be able to do anything. So I will give you some examples later why we need cloud computing, why we need some of these AI tools to help us to process data. And so this is just a small GitHub organization. And this used to be under my personal GitHub account, but some of the packages are being used by some government agencies, some companies, staff. They want to use these, but they are very concerned that I'm the only one. So if someday I disappear, it's not sustainable. So I say, okay, fine, maybe let me create a GitHub organization and then move things. So if anyone is interested in, you're welcome to contact me. I can add you as a member. I also welcome any project. If you want to host it here, just let me know. We can host your project on here. So it's not just me, but yeah, right now it's only like less than 2,000 followers. It's not a big audience, but certainly some of the packages that be used by thousands of people around the globe. And so first, let's talk about Earth Engine and GMap. So how many of you have used Google Engine? Maybe rough half. Okay, that's great. So if for those of you who are not familiar, so Google Engine basically is a cloud computing platform for doing large-scale geospatial analysis. It's different from Google Earth. So Google Earth is basically for viewing images, but you cannot really do any computation. Google Engine basically you can think about is a computing backend behind Google Earth that process a lot of data, but it's not just for high-resolution imagery. We have a lot of satellite data, and Google Engine is free for research and education and also non-profit. They also have the commercial offering if you're using for commercial. And so why do we want to use Google Engine? So especially in academia, you can look at the bar plot on the right, right? So Google Engine was initially created, I think, in 2010, so it's 15 years now. They started the public basically sign up, I think, in 2014. So it's 10 years roughly 10 years now, and you can see the exponential growth of publications using Google Sensing. So it definitely probably the most popular cloud computing platform being used in geospatial because it has done a lot of heavy lifting. So you don't have to worry about how to do parallel processing, how to download the data, how to put things together. All you need is just a couple lines of code. You can access to tons of data. Just like you're watching YouTube, you're watching movies on Netflix, right? You never have to worry about where's the server, how do I set up those backend, and then so people can watch. All you need is just open a browser, and then you can just do a search, and then you can stream the movie. Same thing in Google Sensing. Of course, there are also other cloud computing platforms out there, but they're just not as user-friendly as Google Sensing, so not even close. So this is certainly has a large user base during the last couple of years. And one of the biggest advantages is the data catalog. So it has over 100 petabytes and it keeps growing. So 1 petabyte is 1,000 terabytes. So this is not something an individual organization or any individual researcher can host this kind of data. So it has tons of data that allows you to do streaming and also cloud computing. It has API, Python, JavaScript, REST API, and it's free. I cannot imagine this in the past that if I have to download all the data, how to process the data using my computing. It's going to cost you thousands of dollars, tens of thousands of dollars every year. So this really opens up the opportunity for us to do a lot of large scale, global scale, national scale studies empowered by Google Sensing. And it's reproducible and accessible because you can just click the source code, you can generate a link, anyone can open it, and then you can run the source code. So this is also really makes things more accessible because traditionally when you publish a paper in journals, right, you host your data somewhere and then the author need to contact you, like, can I access the data? After some time, you have no idea where's the data you put, the hard drive, date or whatever. Like, but these things, it lasts. As long as you have the link, you can open it, it's there, you can run, you can get the same result. And so I did some like literature search. You can see all the publications. So so far for the last 10 years, these are almost 2,000 papers that has Google Sensing in the title. So they have Earth Engine in the title. So that means it's definitely utilizing that. Upper right corner here, there's a link. So if you want to download the entire list, you can access it. There are also almost 6,000 papers with Google Sensing in the abstract or in the title. So it's still growing. So certainly 2024 is not finished yet. You can see the dip, but I would imagine it's going to actually exceed 2023. So it keeps growing. So every year you have thousands of people utilizing this to do a lot of geospatial research. So it certainly has a lot of impact in the academic community, but also in government and also in the industry. So here's the example. Among those papers, definitely Landsat is one of the most popular satellite missions being utilized in geospatial. And so right now we have Landsat 8 and 9 operational in space, but Landsat Next is going to be launched in 2030, so 6-7 years from now. And the spatial resolution is going to increase from 30 meter to 10 meter resolution. The spectral band is also going to increase from 11 to 26. So 3 by 3, right, 9 times. And then spectral band is also more than double. So it's going to almost 20 times larger than what we have right now. If you're familiar with the file size, right? So this will be kind of the table showing you what's the file size for one Landsat scene, 8 and 9 right now. So compressed about 1.6 gigabyte. So in 6-7 years, it's going to be 20 gigabyte. And I don't think overall computer hardware improving, but I don't think it will improve that many times. So certainly, if you have never used cloud computing, now is the time to basically catch up. Otherwise, when 2030, when the satellite is launched, you'll be just sitting and then waiting to download 20 gigabyte of data to your computer. People are streaming, cloud computing, doing all the things in seconds. So yeah, just be prepared. It's coming, and certainly cloud computing will help us to do things more efficiently, and it's going to save you time and energy to handling and managing the data. So as I mentioned, Google Sensing has a huge data catalog, also over 100 petabytes, and all kind of satellite data, and also land use, land cover, weather, climate. It's most of the popular ones are already out there, and they keep ingesting new data sets, and it's very nice just to think about. These are all free and accessible, so you can utilize any data that you want. And just like Netflix opens up the entire movie database for free for anyone to sign up. I guess anyone just go there to sign up and watch the movie. So this is a huge database. The nice thing, you don't have to download anything. You can just stream the data, and then a couple lines of code, you can access to the entire data catalog. So all you need to figure out how to access the data, and then you can start thinking about the question. So it really lower the barrier. And so traditionally, before this one, we have to think about where do I download, where do I find the data? How do I download the data? Do I have the storage to store the data? If you're doing global studies, you need terabyte data. And do you have the internet? You probably can do that at school, but I don't think you can do that at home. It's going to exceed your quota easily. And even if you have the storage, you cannot really run computation. There's no way you can run terabyte data without having to use a large machine or a high performance computer to do data processing. But this, anyone can do it just with a browser. So so easy to do. And I also created this one called Google Sensing has the so-called spatial temporal asset catalog. So basically, it's a standard or a specification allow us to store the data, query the data, because geospatial data, when you go to any source engine to source data, you can either specify the bounding box, you specify the date and time. It's not different from doing Google search, right? Just doing text. This, we need some geospatial query. So the spatial temporal asset catalog allows us to do that. And I kind of build on top of this a stack catalog, and then provide a table showing you the list of data set available in the Google Sensing data catalog. So it has almost 1,000 data set. Okay, so each data set, for example, one satellite mission is just one data set. And it's a huge data catalog with over 100 petabytes. And so GMap kind of built on top of the Google Sensing API. I created a package around right after pandemic. So at the time, I was teaching my students how to use Google Sensing, use Google Sensing. And during 2020, in 2020, it was like mostly JavaScript. The Python API was not very good, and you cannot even visualize the image like data interactively. So I was so frustrated. At the end, I spent some time learning some mapping library, IPyLeaflet, Volume, and then trying to figure out, okay, how do I visualize the data interactively? And then so I created this package just for my students, just for myself, to teach them easily, and then release on GitHub. And people like it, and then I continue to update it, add new features every week, and the rest is history. So now it's being used by a lot of people. Over 3,500 projects on GitHub use GMap on their projects. It's all open source. You're welcome to contribute to the project. And so last year, Google Sensing officially adopted GMap in their documentation. So now if you're using Google Sensing with Python, most likely you're going to use GMap, because all the examples right now on the documentation also use GMap. And you will see here, import gmap.core as GMap. Basically, GMap has too many functions, and the core is being co-maintained by the Earth Engine team. So it's more stable, it's more robust. They have a lot of automatic testing, but there are a lot of extra functionality that they were not able to support because they don't have the resources. But again, it's free and open source. You don't need to pay anything. You just sign up on an account, and then you can start using that. And then you can just click a link on their website. Then you can open this up, and then you can start streaming the data. So next, I'm going to show you some key features that what kind of things you can do with GMap. So GMap is all about interactivity. So you can just create a map, 2 lines of code, and then you can source data. For example, I want the link cover, and then you can select from the drop-down list, and then just one button, then you pull the data onto the map. Everything is interactive. So you don't actually have to download the data. Basically, you search a movie, and then you start watching the movie. And it has 100 petabytes. Okay, so you have access to over 100 petabytes at your fingertips without having to download anything. You don't have to worry about the storage. You don't have to worry about the compute. Everything. If you're just doing data visualization, there's pretty much no limit. If you're running the computation, sometimes there's limit that you need to think about, because it's free. It's not allowed. You're not going to be allowed to you to do everything. It's some of the things they might not support. You might still need desktop computing, but at least in terms of some initial data exploration, this is the base one you can get right now without having to worry about downloading data and also going everywhere to source all kind of data set. And you can visualize data interactively. So Google Sensing it's vector data, raster data, all kind of data, tabular data. So you can basically, just like desktop GIS, you can load the data with a couple lines of code, and then you can start changing the symbology, changing the main combination. If you ever use desktop GIS, these are some of the standard things. But the advantage about using this, you only need just a browser. You don't need to install any desktop software on your computer that takes gigabyte storage. All you need is you can do that on your iPad or you can do that on your cell phone. It works just fine because it's doing all the data streaming. And so GMAP makes it really easy. So even if you don't have strong coding skills, you can also use it because it's all like graphical user interface. You can also visualize data in 3D. So Google Engine, most of the data is 2D, but I also incorporate some new mapping backend, for example, Mapbox and Map Library, so allow you to visualize, combine multiple data sources together. So you can visualize set data, land cover data with some built-in 3D. And again, this is pretty much 3 or 4 lines code. Then you can see create a map like this very easily. If you want, you can also visualize, for example, in a 3D globe. So this, for example, built on top of Mapbox, just like Google Earth. You have satellite imagery, but we can overlay all kind of satellite data layer or land use, land cover, whatever data layer you want on top of the 3D globe. So it's much better than just doing the 2D visualization. And so these are some of the, again, I want to point out, so all the demo that I'm showing here, you can click the notebook in the upper right corner there. There's a link. You can go to the hyperlink. You can sign up on an account and then you can run it on your own. So everything is pretty much reproducible. It's very simple, couple lines of code. You can also create time-lapse animations. So there are lots of satellite data running in space that capturing data continuously. And all you need is just create a map and then go anywhere around the globe, simply draw an area of interest. Then you can create animation like this in 20-30 seconds. A nice thing is like different from the Google Earth time-lapse that's only RGB and also coarse resolution. This one you have full control. You can use any satellite as long as you have the time series and you can create animation like this, super easy. This was not possible without cloud computing. Think about how many data sets being involved because you have to filter the data by the region and then you need to filter by cloud and then you need to create cloud free, remove all the cloud and then to create by year, by month, by quarter. So it's up to you what you want to kind of time series you want to use, but this is very powerful. And without this kind of technology, this would take you hours. A simple animation would definitely take you hours just to create, and it's not that easy. But now everyone can go online and then just run this one within 20-30 seconds, you will get this kind of animation. So these are some of the things you can do. Besides for doing visualization, you can also do all kind of computation. So you can run things at scale. You can create this kind of time plot for your analysis, just a couple lines code. And like I mentioned, it can be small area, it can be large area, it can be global. It doesn't matter. So Google saying you'll be able to figure out the optimal scale to run the computation and then to get this kind of plot easily. So you don't have to download the data. All you need is just some sample code. So these are some of the key features I want to show you. But next, I'm going to show you a couple of features that are relevant to AI and GeoAI. So there's a Jupyter AI Python package that you can install. And I contributed the Google Gemini into the Jupyter AI. If you want to learn more, you can click the Jupyter AI so that you can use open ChatGPT, you can use all kind of model. So in this case, I can just simply ask, okay, visualize the DM using GMAP and Google Engine. It will generate the sample codes in here. So earlier we have a couple talks about large language model, but this one really shows you not just generating the code, but actually running the code and also show you the result and also interactive. The nice thing about this is you can integrate within your Jupyter workflow. So it's not just like text. You can actually do code execution utilizing Google Engine GMAP. And think about that 100 petabyte of data. You can basically ask to write any code using GMAP. Of course, it's not perfect. Sometimes it made up some of the functions that doesn't exist, and you need to actually modify. But I'm going to show you some of the examples that actually can iterate the code itself. If it doesn't work, you will figure it out, and then you eventually give you some working code examples to work with. So this is the initial one that I contributed a couple months ago. And the second one here is this one is called Genie. So this is in collaboration with another Googler, Simon. And the idea is that we want to allow users to ask questions. So for example, this is simply, okay, show me the DM around Australia. And then you will show you the DM. You grab the data and then visualize that. And you also analyze the imagery. So you ask it the question, but at the end, once you present the data, the language model will know where is this imagery located. So based on just the thumbnail of the imagery, you figure out it's Australia, what's the color, what's the palette, and you can say, okay, the color is not good. Can you change the color palette? It will do that for you. You basically can give commands and then turn it into code and then execute. And then you analyze the result and then you will think about yourself, but is the result good enough? Or you can continue to provide additional prompts and then we keep iterating. So for example, it can be DM, it can be temperature, it can be anything. It can be any geospatial data. Again, you can check out the notebook, you can try it yourself. All this is just basically just creating a model. So it's just one line of code. And then you have this interface that allows you to explore. So you can keep asking questions. So this is like in conversation mode. So for example, okay, show me the temperature for the last week. You will pull the temperature data from the last week and you will do the visualization. So this is pretty much no coding skills. Anyone can do that because just one button and then you can start asking questions. And you will use Google Sensing, the huge data catalog like I mentioned, the stack catalog. That one has spatial temporal context. So when you ask the LM the questions, you will turn that into geospatial context and then retrieve what kind of data is suitable for your questions, and then you will figure it out for yourself. This is just a simple demo. There are lots of potential applications. As I mentioned, it's very powerful because it will fix the code itself. So if you get the sample code, if it's not working, and then when you run into errors, you will go back to revise it until the code works and then provide the example. So this is really helpful because sometimes if you're working on a research project, you have to think about what data do I use? Where can I get the data? But now you can just simply ask, okay, I want to analyze the temperature for the last decade. It will do that for you. Although it's not going to be perfect, but at least you get some initial one. You can quickly think about if there's something, there's a certain pattern that's obvious in the region, in the certain time frame, then you can use these initial samples to follow your research questions. So this is another one, and the last one that this is a new one that just added last week. It's called Google Sensing Data Explorer. So it's built on top of the 100 petabyte data catalog, the stack catalog, and you can ask any question. For example, basically give you a suggestion, what kind of data set can you use? So you can just simply ask, okay, I want to, how has the global surface temperature has changed? You can give a spatial location, you can give a time frame, last decade, the whole century, whatever you like. And then we go to the data catalog to figure out what data is suitable for doing this kind of time series analysis. And then you can just select from the list, and then you will show the data interactively. So in that way, you don't have to, you will show you all the sample code. And I can also ask how has the surface water changed in a certain area or at a global scale. You will show you, for example, this data set is not suitable because it doesn't have the time, the time series component. And for surface water, one of the popular one is the JRC Global Surface Water. So you show you the spatial resolution, the time span, and all kind of information. So this is certainly useful for users that are new to a specific domain. For example, water, forest change, whatever you like. You can just ask and then you give the question. Rather than you have to go online to search Google everywhere, like, oh, what data set should I use? Does it cover this area? Does it have this time series component? And you can also ask it to analysis. So behind the scene, it's going to use the data catalog, the stack catalog, to figure out the data set to use. And then because most of the data catalog has the sample code for JavaScript, and Gmail automatically convert the JavaScript to Python. And then you execute the Python code. And sometimes it's not going to be perfect because if you're converting from one computer language to another, sometimes it's not like perfect conversion. Then you will try to fix the code itself and then eventually give you the working code examples, and then we execute and then show you the map. So basically turning from just text prompt to executable working Python examples, visualizing geospatial data, and also do analysis. This is just the starting point. There are a lot more things coming that we can ask it, for example, so how much global urban area has increased during the last decade, okay, or the last 40 years. And you will be able to actually do that for you. And eventually we're going to create those graphs, for example, without you to do it yourself. And just a disclaimer, this is all automatic, so it's never going to be perfect, just like ChatGPT. So you have to be cautious about the result. But at least you can give some initial prototype to get started. And for people that without coding background, this is maybe a game changer for them because now they have access to 100 petabyte of data. And they can see it, they can run some initial result, they can create some animation, So it's actually really lower the barrier for people to do geospatial and also GeoAI. And so those are some of the features I want to show you. There are a lot more. So if you go to the gmap.org website, there are over 100 Jupyter Notebook examples. So every notebook introduced some new features. And last year, I also published a book about GMap. And you can check out the link there. It's all the examples are free accessible. If you want to purchase a hard copy, you can check out the link on the left side. And this is last year, and all the AI stuff that I just saw is actually not in the book because things change so fast. So I might need to revise it to add those new features. But you can certainly just use a browser, have an account, and then you can try things out yourself. And I would like to acknowledge the funding support from NASA for the GMAP project, and also Google for their support on some of the work. So I have been collaborating with them on some integrating some of those AI features into GMAP. So we are proud that GMAP is funded by NASA among some of those big popular geospatial, not geospatial, Python packages, NumPy, Pandas, and Matplotlib. And I will continue to maintain and support the package, but we welcome contribution from the community to keep it going. And the next one I'd like to talk about is the segment NEC model. So this is the one that's earlier the text to segmentation model already mentioned. So it's a very popular model that was released last year by Meta. So it was April 5th, 2023. So it's only 1 year and a half, but you can see the paper, the citation over 6,000. So that paper has more citations than many of us, like in our lifetime, for your entire career. And you can see how popular it is because it's a foundation model that can be utilized by many domains, including geospatial. And the idea is very simple. Give the model an image, it will give you the segmentation, although it doesn't really know what it is. It just segment similar pixels into groups. And I don't have time to get into the details, but here's some of the kind of demo showing how it works. And they have the so-called image encoder, basically turn the image into a NumPy array, and then you can have some input prompts, point, bounding boxes, and text prompt, and then we give you 3 output masks. And then from there you can pick, because sometimes if you just give 1 point, you don't know whether, for example, put a point on my face. Are you trying to expect my face, my forehead, or my entire body? And so the model can give you 3 output masks for you to choose, but you can just we guess you give it the highest probability, so you can just extract 1 mask if you want to. And this is kind of demo that I took on the website. They have so-called automatic segmentation. So you give an imagery, it's going to generate those grid of sample points, and then you're going to group them together, kind of like doing object-based region growing. And then you organize, group similar pixels together, and then give you a mask. And so one thing to point out, it doesn't know it's horses. It just knows that it's an object, like very much similar with those similar pixels. So this is called automatic segmentation. They can also use input prompt, so you can place a point on the imagery, and then we extract basically the pixels surrounding the image as a single object. So if you provide a point, most likely you know what object it is. So this is kind of like a hybrid segmentation, or like the first one was unsupervised classification. This one was is like unsupervised. This one is kind of supervised or hybrid classification. And so you can provide a couple points, and then you extract all the things for you. You can also use bounding boxes. So you can draw a bounding box. You will extract the object inside for you easily. You can also do text prompt, although this one was not released by Meta. It's other people extend this one to provide some text prompt capability. So this is basically from the model, and also release all kind of data. So like I said, the model doesn't generate, it only generates the mask, but it doesn't generate the label. So you don't know what it is, but you can always do some post-processing to assign classification label if you want to. And they also release the data set. So this is very powerful because it's a foundation model, but you also provide the data that allow people to fine-tune the model. And you can check out the website, and also they have documents about where do they collect the data from. So it's a segment anything 1B, so 1 million masks. So it's a lot of data, and it's coming from a variety of different regions. So it covers the diversity. So that's why it's foundation, because it has seen many things. And so it's zero shot. So if you give an image that I have not seen it, it can still figure it out itself. Just like basically ChatGPT, but it's in computer vision. It's the first like really major foundation model that can do segmentation without you provide any training data. And 2 months ago, then Meta released the second version. This is called SAM2. So you extend from the first version that only do segmentation imagery. Now you can do video. So it basically adds a memory in those images. Think about if you can segment one imagery, you can segment another one, and then you try to find the relationship between those adjacent frames. And so it was able to actually do segmentation on video, and it's even more powerful. And the model actually becomes smaller, but it's super efficient because you can do real-time object checking and segmentation. So there are a lot of people actually adapt this one to other image segmentation tasks. It still works on imagery, but you can provide a video. So think about video, like for us in geospatial, we don't really do video, but we do time series analysis. It's the same idea. At the end, all the deep learning model is just dealing with numbers. So you can always turn video images, so time series into numbers, NumPy array, and then you can fit into the model to do segmentation. You can check out the paper here, and this is kind of the architecture, how it's doing that. So you can provide an imagery, and then this is just only imagery. So similar to the segment anything model 1, but model 2, you will see later you add more stuff into that. But the prompting are very much similar. So you can give a point, you can give a bounding box, you can give some text. Again, text is not implemented. They just say they can do that, but they don't provide actually that. Other people build on top of this to do like segmentation on video using text prompt. And you can apply the video, so you can see here the memory attention. So you can actually, the extra memory things into that, and it was able to actually refine. So when you're segmenting the video, if sometimes the object is kind of disappear somewhere in the middle, you can go back to that frame, you can add the point, and then we pick that up. So it's very, very powerful, it's very flexible and easy to use. And this one just show you some demos like that, right? So on the left side, you are checking, for example, in the soccer, and also a certain foot of the person. You will see it keep checking, but sometimes it makes things up. You can add another point, or you can remove something that you don't want to. So anything within that time frame, you can add things, you can remove things. So it's very, very powerful, very, very fast. And that's about kind of instruction. And next, I'm going to talk about segment geospatial. Built on top of this model that allows you to do segmentation on satellite images, remote sensing images, and also time series, just with couple lines code. So I want to point out that the same model, the segment anything, is not trained on geospatial data. It's trained on regular photos, computer vision. It has nothing to do with geospatial or remote sensing. But we can actually use the model to do something without having to fine-tune the model. It works pretty well. It's not perfect because it's not trained on geospatial data, but I can show you some demo how it's like doing that. And so I created the package last maybe May, like one month after they released the same one, and it's open source. You're welcome to contribute to the source code. It's quite popular. It's like within a couple of months get thousands of GitHub stars. And certainly a lot of people are adapting this one to do some initial experiments with segmentation on geospatial data. So next, I'm going to show you some demo. Again, all the demo has a notebook link there. You can try it out yourself on Google Colab using GPU. So everything is reproducible. So you can basically segment anything. For example, just provide a set of imagery. You segment it for you. And this one is all the greenhouses. It's very colorful. Again, it doesn't know it's greenhouses, doesn't know it's houses, it just know it's some object, that's it. And you can do, for example, agriculture field boundary, right? You can also segment. And so all the model basically give me a geotiff, give me a geospatial imagery, remote sensing image. I output the geospatial data for you. It's not just, now it's not a photo, it has geospatial information in there. So behind the scene basically is get the imagery and then turn it into NumPy array and then fit into the model and then do the segmentation. And then when the spill out data, I add the geospatial information back into the imagery. And this is automatic segmentation, so you don't need to provide anything. It will do that for you. There are a couple of parameters you can fine tune. If the result is not perfect, you can do that. But this one, usually we don't use it. Again, you don't know the label. It's just like some colorful object, but it's nothing. this is one that really relates to our geospatial, is that we can use point coordinates. So you can, for example, I want to extract the buildings. You give me the imagery, and then you can give me a couple points. Or you can, for example, in this way, you can do interactive segmentation. So I just pinpoint, place a marker on the map and the building. It will extract for you and see how far this is. This is like real time. So I can just pick the object, place a couple points, and then I can save the result. Output is GeoTIFF. You can also output is vector data, and you can also do some post-processing to do cleanup. You can load some existing points. So the points can come from your field data. You can come from your existing data, and then you will be able to do that for you. You can think about, you have the point for some buildings, some trees. It keeps growing, but the object location is still there. You can use this one to do segmentation, and you can output the bounding boxes, also the rectangular, and you can do things interactively, or you can do it in a batch mode. So you can just provide a GeoJSON file. For example, give me the imagery and give me a GeoJSON file of all the points, and then you will do the segmentation for you, output the raster imagery, and then you get the mask. And you can also, all the output vector data have all the geometric attributes. So you know the size, how many pixels in there, what's the area, and what's the geometric attribute, what's the eccentricity, elongation, all kind of geometric attributes are automatically calculated. And you can also filter out small objects. You can filter out the whole. So there are a lot of functions in there that can help you do the post-processing. So you can try it out. So this is using point coordinates, input geospatial data, a vector imagery, a vector data set, and also a raster imagery, and then output raster imagery and also vector data of the segmentation result. You can also do bounding boxes. So for example, you want to extract trees, and the bounding boxes for many of the deep learning models, they usually output the bounding boxes. So you can use the bounding boxes as the input prompt, and then we segment all the trees. So think about this one. If you have to manually draw the tree boundary, it's going to take you a while. This one takes like less than a minute. I mean, probably 10-20 seconds, like to run, initialize the model, and then take you 10-20 seconds just to get the result. And again, you can calculate the size, you can calculate how many pages, and then you can do the visualization. So it's very easy to use. You don't have to worry about doing that manually. Yes? Oh, the bounding box is coming from input, so you can provide input. So what I'm saying is there are some deep learning models that can output the bounding boxes, but they cannot give you the accurate segmentation result. Just like I talked earlier, Dr. Mai mentioned that other deep learning model can do the detection, can give you the label, but they cannot depict the boundary very well. So in this case, you can mainly draw the bounding box, or you can provide just a GeoJSON file of all the bounding boxes, and then you will basically refine. Nice thing about this is the bounding box doesn't have to be perfect. It can be slightly offset. You will still be able to figure the object intersecting with the bounding box. So extract all the trees. Again, there's a novel example there. You can click the link. You can try things out. You will see how it works. So you can do just provide the coordinates. You can provide a GeoJSON file. You can provide all kind of things. And it's super flexible. So you don't have to do those conversion back and forth by yourself. So SamGeo handles all of those. And this is another one called using the text prompt. So for example, give a set of imagery. I can just ask, okay, buildings, you will extract the buildings. I can ask trees, you can extract the trees. So this is similar to the presentation by Dr. Mai about using the text to segmentation. This was contributed by another contributor, Lucas Osco, but he used the language segment anything model to do the segmentation. But the idea very much similar. Basically, give me the text prompt, and then use the grounding Dino to basically extract the bounding boxes. And then basically it's a two-step process. Give it the bounding boxes, then use the bounding boxes to fit into the model, and then give you the result. So this is very, very useful because not many people know how to build the model, how to train the model, and just give an imagery and then ask anything. Again, it's not perfect. Anytime when anything's fully automated, you're going to get either some good results, sometimes garbage. But as the demo shows, right? It works pretty well. You just need to find optimal parameters, and then you can refine them there. You can get the initial result. You can use that to fit into the model again. It will refine the result. So save people a lot of time. So if you're doing some simple mapping, this give it a couple seconds or a couple minutes, you can get the result easy. Again, input geospatial, output geospatial. So it's not just a simple JPEG. You can overlay on satellite images, and very useful. And this is another example. For example, you want to detect all the swimming pool, just type swimming pool, you will be able to do that for you. And again, you need to have GPU, otherwise it's going to take you some time. There's a notebook there, you can try things out. So the text model is usually suitable for detect large object. If your object is very tiny, probably it's not going to work very well. Again, none of these models are being trained on geospatial data. It's just trained on regular photos. So large object, because those photos usually have very high resolution, so it works pretty well. For small objects, it's going to be, if we ask to detect cars, I don't think from this image itself, if human cannot see it, the computer model won't be able to do that much. It won't be to improve the accuracy that much. But this is kind of the experiments that you can certainly can do. So the next one, this is a newer version built on top segmenting anything model 2. And this one is like you can do segmentation on time series images. And as you can see, I have this lane set time series for 40 years. And so all I need to provide is the marker at the bottom here. So just 3 points in the first year. You can do 1 point or 2 points. It's up to you. You can add more points. But the idea is that all I need is provide 3 points in the first frame, and extract the reverse, and then you propagate for all the time series. So you don't have to provide training points for all the time series. All I need is just 3 points, and you do it for you because it has the memory. It tracks how the object is evolving. Again, this is just the demo. It's good for detecting large objects, but for smaller ones, you're going to basically need to add more points, markers. So and see how powerful it is. Like traditionally for doing remote sensing, if you want to extract water, you need the NDVI, NDWI, the normalized difference water index, or some other things to actually extract the water. And they need to apply for every images. But now I don't have to. Just any frame, you can add more points. If it misses something, if it detects something that it's not supposed to be, you can add a marker that's negative, and then it will remove that. So you can detect, for example, rivers, vegetation, buildings, or anything like that. So this is another example. For example, you can see this is also landscape imagery, right? So this is the RC in Central Asia, and all I need is basically just 2 points in the first year. And so the green star there at the bottom, those are the input prompts. So if you provide the input prompt, you know what class is, what label it is. And then you segment the entire time series for you. Again, input the geospatial data, output the geospatial data. So this is not just a video demo. It actually behind the scene is a set of images in a directory. And then we output another set of images in the output directory. It's all geospatial, but it's with the mask. And then it's a binary mask. Then you can use it to calculation. You can figure out, for example, in this case, how much has the water lake strength in the past couple of decades, right? And this is not something you can easily do like within a couple of seconds, but now this is automated. So you can do that like within a minute rather than have to spend hours trying to do the algorithm yourself. It's very, very powerful. So this certainly has potential for being applied to geospatial data. And it's not just geospatial because you can do any object detection. So in this case, you can have videos, you have drone imagery, tracking cars, tracking anything, and then all you need is just provide 2 points. So for example, the input point is just 2 points at the bottom there in the first frame, and then press the marker, and then we keep track of the objects throughout the entire time series. And again, you can output the data in video format or G format, or it can be, if it's geospatial, then it will be geospatial output. So the last example I want to show you here is, for example, this is from a GHOST satellite from Norway, and it's the volcanic eruption. So again, you can just place simple points in the volcanic eruption, the epicenter, and then you will detect object for you. It will keep track the size. So this can be used to monitor, for example, hurricanes, volcanic eruptions, or anything. Anything can be captured by satellite data. Satellite data will be able to actually do that easily. So all you need is just provide the pointing to the directory of the folder that contains the satellite data, and then we do the segmentation for you, and then output the series of images for you. So and Yeah, so I would like to acknowledge some of the support from Amazon when I was working as a visiting academic there. So I spent a lot of time developing the SEMGeo package to make it easy for people to utilize it to segmentation. And lastly, I want to show you some additional resources. So I do create a lot of video tutorials. So you can check out my YouTube channel with over 700 videos, and also a lot of courses that I'm teaching is all online. And for segment geospatial, I have this couple of tutorials that teaching how to do segmentation using SEMGeo for different type of images, and how to get the result easily using the novel example that I show you. And I also teach GS programming intro in my department, and I put all the things online as open access, and also all the videos. So if you want to learn more about some of the Python programming, how it can be utilized to do visualization analysis, you can check out the video. It's all free. So the class is still ongoing. So I post a video twice a week when I'm teaching in class, or record a video, and you can check out then. It's all free, and you're welcome to adapt to your old project or your teaching. And last one I wanted to point out is the Maxar Open Data. So Maxar released a lot of high resolution satellite imagery for natural disasters. So if you're looking for some high resolution data for doing GeoAI machine learning, this is certainly a very valuable data source they can use, especially doing segmentation. So you can check out the data catalog that I created. Makes it easy for people to visualize the data. So the next couple examples, for example, the flooding in Libya last year. So you can easily figure out what data available released by them, and also how to easily visualize them, because these are very valuable data, but it's not very easy to use. Not many people how to like source the stack catalog, how to filter the data, how to use a S3 bucket, how to access data. But you can try out this interactive web app, and you can see the data very easy. Or more recently, the Hurricane Helene and also Milton, they released the imagery. So you can easily go there, check out the before and after the event, and how it's impacting the community, how you can utilize some of those to do geospatial. So my goal is to make this kind of data set more accessible, but in the meantime, also provide some of the tools that allow people to run analytics on some of these open access data. Okay, so that's what I want to share with you. Feel free to connect with me if you have any question. Thank you very much.